are live. Great. Okay, and now sharing. Perfect. Okay, so as I mentioned that today is TDA plus X, where X is graphs. There's two separate topics. First of all, I want to talk about how do you use persistent homology to help with graph visualization. So specifically, how do we utilize barcode, which you have seen hopefully throughout the whole semester? How do we use barcode to guide the force-directed layout of complicated graphs? So we're going to see some animations. We're going to see some sort of description of the methodology behind it. The second part of today's lecture is about using, again, persistent homology to look at brain networks. I kind of mentioned it in a few lectures before, but I would like to go deeper into it and explain how topological features can be integrated into a regression framework, and how do we think about topological features is helping with sort of regression. So so I got some question from sort of students question over Piazza about, okay, I have a data set and I applied my topological tools, especially a certain form of kernels. How come my classification result is not very good? Okay, so I think one thing that we need to understand is that topological tools is sort of many tools along the data analysis pipeline. There is really no reason to believe for a particular data set, the topological feature is going to be the silver bullet, right? So in a sense that it's unless there's a very strong indication, there's the data is very geometric oriented, I think it's not a safe thing to always assume topological method by itself is going to be the best one to be used for classification or regression tasks. And oftentimes, as we see in the second part of today's lecture, is that you can actually want to combine topological features with some existing features for classification and regression. Does that make sense? Because sometimes, when you have a hammer and you want to find the nail where you can use a hammer on, but it's not always means that the hammer you have, which for example is a particular kernel that is based on topological features, is going to be the best hammer you have for that problem. So as part of the final project, I think some of those projects really try to explore the strengths of topological features and then the strengths of topological method in analyzing a certain data set. And oftentimes you might have to combine the topological information with some prior knowledge or other existing tools you already have for the data set. So it's hard, for example, if you think about even for shape classification, right, where people just using sort of the topological feature coming from elevation function, for example, as a feature vector for the shape in shape classification. And then what they can do is they can kind of match the state of art. They didn't necessarily beat it, right? So it's hard to imagine, for a certain problem that the topological feature is always going to beat the state of art. So that's something to keep in mind, okay? All right. So graph join. So this is a joint work with a bunch of my collaborator and especially Ashley, who's the lead author in this piece of work. So the idea is as follows, is that, graphs are often used to visualize network data. On the left-hand side, it's sort of, it's sort of a force-directed layout of some post-rebuild site. And the idea is that there is always some sort of complex relationship you're trying to capture. Specifically, you can model social interactions, you can model computer networks, you can model traffic systems. And the classic one is what we are showing here is node link diagram. And basically the entities are the node, and their relationships are the links. Okay, so that's very popular to visualize graphs. Of course, there's other ways to visualize graph. For example, you can visualize graph as matrices, where pairwise entry in the matrix corresponding to the connectivity. So, but today we're going to mostly focus on node link diagram, and specifically force directed layout. So force direct layout is some form of automatic graph layout, and it's also it can be interactive, because what you do is you kind of use local relationships to try to obtain the global shape. And then the main idea, next slide. The main idea for sort of force direct layout, if you look at sort of the right-hand side, it's kind of moving a little bit. Hopefully you see the animation, all right? So what happened is that essentially for force direct layout, there is a force. You're treating the node link diagram of the graph as a form of spring system. And then there's some force, which is attraction force and repulsive force between pair of nodes. And then the idea in the force direct layout is actually trying to obtain a balance, like a local minimum of that system. So for example, what you see here is that, this animation is showing that, as you're running the force direct layout, the node is still trying to adjust its location a bit to try to arrive at a local minimum. Okay, so this is a repetitive loop. At some point, it's going to stop because it reached a local minimum of sort of the energy that come out of the attractive force and repulsive force among the nodes. Okay, so this graph happened to be a complete graph, which means that every node in there has a connection between them. And this actually is coming from the US Senate anti-voting data set. Okay, this is 2008 US Senate anti-voting data set. So it's basically if you look at it's part of the public record for the year 2008, you can look at for each Senate what they vote against for whichever issue it is. So for every single Senate, it's actually, you have, if you look at the table on the left, for a particular issue, they can vote, nay, yay, or they're not voting. Okay, so those are sort of their voting records. And it's an interesting data set. It's basically looking at how US senators voted against each other. Okay, and but it's very difficult to kind of decipher from the visualization, because this is one of those classic things where the visualization is very cluttered, and it can be dense. And in this particular case, it looked like a hairball. If you look at the picture on the right, the red corresponding to Republican senator, and the blue is a Democrat, and then purple is independent. Okay, so when you're visualizing it, use the classic force-directed layout. Even though it arrived at the local minimum, you just saw this nice ball, right? So what we want to see is can we use some form of user interaction with respect to this initial layout to try to group things together when they are very similar and put things apart when they are different. And of course, you want to kind of do this automatically, because if you're just having this network, if I just push and drag, if I say, oh, well, I think I have some measurement of the Republicans to be voting very similar to each other, Democrat to be voted very similar to each other, I can drag and move. It's not going to be very efficient for large networks, because you want something that is at least semi-automatic. So that's where persistent homology comes in, okay? So that is what, driving force in terms of, before we talk about force-directed layout, they actually have different sort of variations. For example, in here, there is multiple versions of automatic layout algorithm. On the left-hand side is what's called SFDP, scalable force-directed placement. The middle one is called NATO. The right one is FM3. Those are basically very flexible versions for force-directed layout on large graphs. And if you're interested, you can kind of look at their corresponding paper, but they are always sort of suffer from some aspect where there is a situation where unrelated part of the graph can still overlap on top of each other, right? So for example, in the previously in this picture, almost all the information among the senator anti-voting are kind of overlap on top of each other. I cannot really get information out of it. And the same thing, even if I apply the SFDP, NATO, and FM3, even I apply some more advanced forced derivative layout algorithms for the Senate data set, I'm still going to see this hairball because it's a complete graph, and none of those existing techniques will be able to kind of get out of the insights that is underneath the data. So we would like to be able to explore the structure, kind of interactively, and that's where persistent homology comes in. Okay. Well, there's also, before we dive in, there's also other related work that is using some sort of topological information for graph layout, right? So on the left-hand side is what's called topo layout. And in the middle is called click persistence. On the right, you have seen this picture before, is our time varying graphs. So in this particular case, especially the right-hand side, that's where I mentioned before the persistent homology comes into play, but in a different way, where we're for every time step of the time varying data set, we obtained a persistent diagram, and then compute the distances between the persistent diagram, and then reproject those time instances of a time varying graphs based on MDS, which is a dimensionality reduction, to look at the clusterings among those time steps. And then the idea is the one when I project it as one-dimensional MDS, the one that is on the sort of on the tip of this one-dimensional curve on the right-hand side, corresponding to interesting time instances where the time varying graph is deviating from other graphs, right? So essentially you want to use it to detect events that is happening for the time varying graph. Okay, so there's multiple existing work that has used some sort of topological information in there. And this is actually what's what happens for if we're using persistent homology to guide. So essentially we want to use a persistent homology feature of a graph in two user selectable ways for the forced derivative layout. First, on the left-hand side, if you see, this is actually the barcode, the zero-dimensional barcode of the corresponding graph on the right-hand side. And this is, again, it's a classic social network example. And actually, it's about characters from Hugo's novel. And then on the left-hand side is a persistent diagram. And then users can sort of interact with this persistent diagram. Let me see if how come I don't have animation? Just a second. Well, maybe the animation will come later. But anyway, so on the left-hand side is the persistent barcode. And you can see that, can people see my mouse? Oh, wait, I'm trying to get my mouse somewhere. Hold on one second. This should be a video, maybe not. Right, so at the left-hand side, you can move that bar. There's a sort of a flag post that you can move from left to right. And you are moving from left to right. You are actually contracting different parts of the graph based on the barcode that they gave rise to. So essentially, we can kind of, when we select a persistent feature on the left-hand side, which is a particular bar, what we do is we modify the underlying forced derivative layout by enforcing a strong attraction force between the nodes that give rise to that bar. Okay, so I don't have my iPad right now, but the idea is the following. If I have a weighted graph, one way to think about how to generate a persistence barcode is by sort of treating pairwise distances, or treating the weight and turn it into a pairwise distances. And by doing that, you can imagine the zero-dimensional barcode corresponding to the minimum spanning tree of the graph, right? So when two nodes are very close to each other, they are merged first if I were going to compute the zero-dimensional persistent homology, right? So the minimum spanning tree of the corresponding weighted graph, where of course we turn the weights into a distance. And one way to turn the weights into distance, well, usually, for example, in social network, there is a high weight between two nodes when they interact very frequently, which means they are somehow very closely related to each other. One way to convert it to a distance is actually takes 1 over that weight. So we kind of invert the weight so that, the higher the weight, the smaller the distance. Okay, so now based on that, you can compute a minimum spanning tree among all the nodes based on this distance. Then the corresponding barcode, zero-dimensional barcode specifically, corresponds to the minimum spanning tree among the nodes. So because it's zero-dimensional persistence barcode, you can actually contribute each bar to a particular edge in the graph. Okay, and that edge connect a pair of nodes. So what happened is that as I move this bar from left to right, this flag from left to right, I am basically saying that any pair of nodes who give rise to the barcode below a certain threshold will be strongly attracted to each other versus, the other one remains stable. So the idea is I'm just using persistent homology to guide sort of the grouping of the nodes, which I deem to be very similar. And then that grouping is done mathematically through the persistence they give rise to, okay? And another aspect is that I can also, for each of the bar, because each of the bar in the barcode is connecting a pair of nodes in the graph, I can also have another operation. Remember, force-field layout has two types of forces. One is attraction force and one is repulsion, right? So attraction happens especially between nodes, which is connected by an edge. But repulsion can happen. You can also enforce repulsion between two nodes that is connected by an edge. So the bar can also be used as repulsive force because you can imagine I can push the nodes that connected by that bar against each other, sort of push them away from each other. But also remember, I'm operating over the minimum spanning tree. So if I pick an edge from the minimum spanning tree, which corresponding to a bar in the barcode, if I push the endpoint against each other, push them away from each other, I'm actually pushing two parts of my graph apart from each other. Because basically you can classify the nodes based on whether they are in one side versus the other side of that edge that is part of the minimum spanning tree. Okay, does that make sense so far? Okay, so that is a two type of interaction you can perform with respect to the barcode. You can filter through the barcode where all the nodes that give rise to barcode that is below the threshold are sort of attracting each other, so they kind of start grouping. And also you can operate of repulsive force, which is a second interactive operation, where for some nodes that is, sort of connected by, for example, very large bars, I want to push them away from each other, therefore kind of pushing two parts of the graph away from each other. So you can use the barcode as sort of interactive tool to introduce additional attraction and repulsive forces. Okay. All right. So I think, so we have talked about persistent homology. You can ignore the first part. The persistent homology for graphs, especially if you can map the graph into an arbitrary metric space. In our case, we're just mapping the graph where a pair of nodes, their distance is their shortest path distance. That's just one way to map them into a metric space. Once you map them into a metric space, you can compute the persistence homology of it. So in this case, if I'm using shortest path distance, then the persistent zero-dimensional persistent homology corresponding to the minimum spanning tree in that metric space. Okay. And this is the part I was trying to emphasize, is that, in this particular case, when I'm looking at, for example, a social network, I usually have it as weighted, meaning that, for example, A and B have an edge with a high weight when they exchange many number of emails. Okay, so high weight means that they are very relevant to each other. So, so what we do is that we actually going to convert that weight back into a distance by inverting the weight. So basically, I'm changing the weight to be 1 over the original weight, and I'm computing shortest path distance. Okay. And then another connection is that I'm talking about minimum spanning tree, but if you think about, I have a bunch of points in the metric space, the minimum spanning tree also gives me single linkage clustering, right? Single linkage clustering is basically, I want to merge things that is close to each other first. So single linkage clustering also is equivalent of zero-dimensional persistent homology in this setting, okay? And then this is sort of the operation I want to show, is that, so on the left-hand side, if you actually look at the graph here, the graph is, here I want to look at the spanning tree of this graph on the left, okay? So what happened, remember, I'm inverting the weights as 1 over the weights. So the spanning tree is going to connect V1, which is a pink node, to V2, which is orange, yellow node, V3, which is a purple node, and V4, which is a blue node. That is sort of the minimum spanning tree if I invert the weights, okay? And in the middle, this is sort of the persistent barcode. We use a little bit different visualization of the barcode. If you notice that, each of those segments is still a bar, but what happened is that I also put a color in between, which basically says that this particular first bar, like the top bar in there, is actually correspond to, because it's connect to two nodes. This bar corresponding to the bar that connect node, the purple node and the green node, so the blue node, which is node 3 and node 4. This is a bar. The second bar is a bar that corresponding to edge that connect the yellow node and the pink node, and so on. Okay, so this gives you some idea of, if I want to do repulsive force, how this repulsion happen between our pair of nodes. Okay, and now what happened is that, if I click a particular bar, if I select a particular bar, it will split the edge from the tree and create 2 subsets. And we can use those 2 subsets to add additional contraction and repulsive force. So for example, on the left-hand side is that if I select, left-hand side is a persistent barcode. On the right upper side, if I select a particular edge, I kind of remove the associated edge from the minimum spanning tree, and I kind of create 2 node subsets, okay? So for example, in this case, I selected the orange pink bar, which is the second bar. I kind of remove it from the minimum spanning tree, and now my underlying graph is actually, nodes in the graph are separated into 2 classes. And then, for example, if I remove the third edge or click on the third bar, I'm removing the edge that's connecting the orange and the purple node. And the idea is, once I select that barcode, I'm kind of enforce either an attraction force or repulsive force between the nodes in the 2 sets. And then using the persistent barcode by the minimum spanning tree, we can also try to capture try to give the users the ability to interact with the graph by selecting persistent feature from the barcode to manipulate the graph layout. So there, like I mentioned in the previous slides, we can add strong attracting forces to contract features. For example, on the left-hand side, if I select, when user select the bar from the barcode, and if we select it for contraction, then we basically add a very strong spring force to the edge that we just removed. So in this particular case, we removed edge between the pink node and a pink node and an orange node. In this case, I'm trying to, oh, actually my label is opposite. In this case, on the left, I'm actually adding contracting forces, which kind of force them together. So, okay, ignore my label. My label is just exactly opposite. The left is adding repulsive force. The right is acting, contracting forces. So the idea is each time I select a particular bar in the barcode, I'm forcing the two parts of the node set to be either attracting or repulsing from each other to change the underlying layout. Okay. So let's see this in action. Okay, so in this case, as I'm moving from left to right, I'm trying to add contraction forces between nodes that is giving rise to a bar. So as you go through, say, bar with small persistence, it's basically try to attract nodes that are connected or very similar to each other. As you increase the persistence level, you are contracting more and more nodes, at a higher threshold. Okay, so what happened is that, in this particular case, you kind of thinking about when I'm going from bar from left to right, I'm in some sense trying to get rid of topological noise in my graph. Okay, any questions so far? Okay, so again, if you just look at the animation, the original graph have this sort of ladder kind of form, and then there's nodes that is very close to each other. So if you think about computing persistence homology, those nodes that is very close to each other corresponding to the ones that give rise to small bar or bars with small persistence. So when I actually simplify or moving my sort of flag from left to right, I'm actually kind of contracting those things together. When I say contracting, I'm not really merging them together. The graph is still graph of the same size in terms of number of edges, number of nodes. The only thing we do is we try to attract to kind of making the nodes that is very similar together right next to each other. So try to enforce them to be, to enforce a large attractive force between them. Okay, and what your end result is, you get a slightly sort of simplified graph. Okay, and then the idea is that in this case, when I'm actually using the barcode, we're actually trying to find or reduce the noise in the structure.
And so, what you end up with?
Yeah, so I'm going to give you multiple examples, right? So the very obvious example, for example, in this case, if you look at the original graph versus the graph that is I have contracted, I'm still trying to preserve some high level structure of the graph, but kind of reduce some of this complexity, right?
So, sorry, with the first one, there's still like sections that seem to not be like, is it actually down to just two elements, like,
oh yeah, so
items?
So to be fair, the underlying graph layout, there's still a force direct layout still happening. So that's why you are not seeing everything collapse to do like one single cluster.
Okay.
So there is still force direct layout at work underneath. That's why your entire graph is not collapsed into like one single node.
Okay.
But the idea is to use the persistence barcode as a way to modify the underlying forces, so that like the ones that is very close to each other, those we consider as sort of a noise, and then we kind of push them against each other, right? Does that make sense?
Yeah, absolutely. That's really cool.
So the next one is to adding repulsive forces. Okay, so for example, in this particular case, there is sort of some pair of edges that give rise to a really large bar in the barcode area. So what we want to do is when we add repulsive forces, we kind of look at the edge that give rise to this large, long, high persistent barcode. And we kind of want to add additional repulsive forces to try to emphasize the differences between two groups, So that's the effect you see, right? So you kind of you kind of change again the underlying force formulation to emphasize the differences between some sets of nodes. Okay, and usually for a particular network, if we're using those two interactive mode, it's usually a combination of both. Is try to highlight what underlying structure is. Okay, and then finally, you can also click on a particular bar to highlight, if I repulse or contract, what are the corresponding two sets of node that bar is responsible of. So when I hover over, if I'm using, say, repulsion, this is to say that the blue set versus the red set are the ones that I'm going to try to push away from each other, depending on which bar I'm using. Okay. And then this is, again, the Hugo's Les Miserables thing. If you look at on the left-hand side, as I am actually going from left to right, again, I'm going to attract nodes that are very similar, which are characters in the novel that is related to each other. And on the left-hand side, we're just using contraction force. And on the right-hand side, I'm trying to use repulsive forces. So the idea is when I'm using the slider over the persistent barcode, we can kind of quickly and interactively cluster the entire graph. And then you can then select bars from the barcode to pull apart some of the tangled features from one another. Okay, and you really, by kind of using repulsive forces, you're trying to highlight the high persistence features. Okay, so you're kind of using the persistent barcode to transform the underlying graph join. All right. And so what happened, of course, there is, of course, how to interpret the final results is that if I'm doing a combination of repulsion as well as attraction among all the nodes, I'm kind of change the underlying layout. And then correspondingly, we can further highlight, for example, on the right-hand side, I don't know how many of you have read this novel, but on the right-hand side, you can, because you are emphasizing selected persistent features, you can somewhat capture important relationship between characters in the novel. For example, there is a love triangle between Marius, Apolline, and Cosette on the upper left corner, and then there is some sort of close bond among Cosette and her caretaker. I'm pretty sure I'm butchering the names, Toussaint. And at the center of the network, there is a Javert, which is a main antagonist who stands between Vaugin and his family. So anyway, so in some sense that, using this barcode manipulation, you can better highlight the structure among a well-known social network, okay? That is coming from the novel. But this is actually the result of the anti-voting, which is actually really interesting. Because remember, from the beginning, you see this hairball, as I am going to use a slider on the persistent barcode to create two prominent cluster. Not surprising, the two prominent cluster are corresponding to the two party, Democrat and Republican. And what's really interesting is that it actually makes the graph a bit more readable and easier to understand, because if you look at the sort of the manipulated layout on the right-hand side, you see that the people who stand out after you collapsing or denoise the layout is that Obama on the right-hand side and Chimney on the left-hand side is surrounded by people from opposing parties. Why? Because those are the people who voted against them for most of the issues. So you can see that most of the Republicans voted against Obama, and most of the Democrat voted against Cheney, right? And of course, it's also interesting to look at the ones that stand out away from the main majority of people. For example, McCain is the one who take a stand where he doesn't necessarily vote along the party lines, but just vote on particular issues and so on. Okay, so this is sort of one of the most interesting sort of story coming out of this is you can actually use persistent barcode to guide how you actually group similar nodes together and repulse different nodes apart from each other to highlight the underlying graph structure. And this is, again, another 2007 Senate anti-voting, right? Of course, if you look at 2007, is that in here, we are specifically focused on repulsive forces. So the idea is we're going to contract low persistent features. We're going to look at repulsing among high persistent features. So you can have a better understanding how each senator voted with respect to each other and against each other. So again, there is interesting clusters surrounding Biden, for example, of how people voted specifically against him in 2007 voting records, anti-voting records. Okay. So there's more, right? So on the left-hand side, this is example of some of those synthetic data. The first column for each of the example is sort of the classic four-student layout, and then the third and fourth and fifth column are sort of our visualization using barcode, by adding both traction and repulsion. And you see that they kind of capture slightly different aspect of underlying data, depends on how you choose which one to further repulse, which one to attract, right? So in some sense, it gives you a lot of flexibility for you to control the forces under the four-student layout to try to highlight the underlying structure. And then the right-hand side are things like real-world networks. There's a bunch of them. You can look at the paper. But the idea, again, is depends on how much attraction or repulsion you introduce to the layout based on the barcode. You are going to highlight different aspects of the data set. For example, if you look at the very last row of this, right? So if you look at the classic four-student layout, is hairballs versus, at least when you are using a combination of repulsion and attraction, you at least see a bit more clustering structure as you see in the anti-voting record we see just previously, okay? And yeah, so there, the code is online and then there is online thing. So any questions so far for this piece of work? Okay, so the takeaway is you can use the barcode from the graphs to guide the graph layout and to highlight the underlying structure of the graph. Okay, so that's one. Go ahead.
I have a question. So the labels right now, so the coloring it's not some kind of clustering on top of the graph. This is just that the labels are known, right?
Oh yeah, so yeah, sorry. The top first row, let me see, I can't really zoom in. The top one where my mouse is, the color corresponding airports.
Right, so these labels are known, it's given from the data. It's not that you perform clustering on.
Yes, all those labels, at least you show here, are known. So for example, the first graph is an airport, different color is different airport from different continent. The second one, this is sort of the science. This is looking at the science literature, publication. So every node is from a particular domain, like biology, biotech, chemistry, or science. So those are well-known labels. But the idea of visualizing with labels is you want to see how does our graph layout kind of separate those labels.
And then when we manipulate the graph, basically what happens is that the repulsive force changes, right, on the edges.
Yes.
And then the contracting and repulsive force changes. So right. Is it possible to do some clustering on top of the manipulated graph? With that?
Oh yeah, you can, because if you actually see it, right? If you combine, for example, let me see my mouse, where my mouse is, this is a combination of using both repulsion and attraction, right? You see that, it's not perfect because you see that some of those color are split into multiple clusters, right? So in some sense that it's not necessarily I want my graph layout to respect the underlying label, but I actually want it to pick out interesting thing. For example, this particular node here, I believe corresponding to like the Hawaiian airport, right? And then it's somewhat, in between Asia and North America. And that's how it's laid out, right? Even though, it has a different color, then it's not green, but it's kind of, to some degree respect some sort of continental structure still.
Okay, that makes sense. Thank you.
Yep. Okay. All right. So that's our first piece of work. And I think this is a good time to take a quick break. We'll come back in 9:58. But any questions? Okay. If there's no question, I'm going to share a different screen. If I figure out how to do this. Here we go. Okay, going to share a different interface. Okay, all right. So the second piece of today's lecture is a bit different. So the first one has a sort of visualization component to it, and to see how to use persistent homology to manipulate graph layout and graph visualization. This second piece is going to focus on, a bit details over analysis of brain networks. Okay, so. And this is actually one of the first piece of work I did in this space, which we're looking at a particular regression problems against using features from networks. So the idea is, okay, so especially for autism, that there is this conjecture that the functional brain networks is sort of related to the behavior measures. So especially for autism, there's what's called ADOS score, ADOS, which is a score that is used to measure how severe autism is, with lower score corresponding to folks who can still function pretty well in society, versus higher score are severe autistic and need assistance. Okay, so the idea is trying to quantify the relationship between the functional network and then behavior. So again, if you recall what's a brain functional network, is that you kind of take images of the brain. Sometimes it's really what's called resting state, where the patient lays in the MRI machine and then they are not doing any sort of tasks. So it's supposed to be resting, but actually it turns out when you are resting, your brain is still sort of functioning and to do all sorts of, you're thinking about all sorts of things. But the idea is to collect the both signal at every single region of the brain. Again, the functional brain network is looking at a correlation between the both signals. So it's essentially boiled down to correlation matrices between different parts of the brain. And the idea is try to use topological feature based on persistent homology and combine the correlation, which is this matrix, with topological features. And the idea is to give a better prediction of autism severity than just using correlation alone, right? So this is an example where, initially when we first started this project, we want to know what is topological feature by themselves, how powerful they are to kind of predict the behavior measure. It turns out you can't just use topological features by themselves. What you will end up doing is actually combine topological features together with the correlation matrices, right? This correlation between both signals combined, they will give better prediction. Okay. So autism, which is sometimes also called autism spectrum disorder, ASD, it's a very important sort of brain disorder that we are still trying to understand. And so far, we still, doctors still does know a cure, and then also it's not clear what is the causes. And then there's no specific systematic method to diagnose the disease, the disorder, but other than ADOS score. Okay, so basically what we want to do is try to correlate the functional brain network against this ADOS score. The idea is maybe down the road, we can use it for early diagnosis or for treatment tracking. So as I mentioned, the functional brain network is representing different brain region and then their pairwise correlation. To compute it, you are going to look at what's called resting state functional MRI. And there's a bunch of pre-processing that is coming from the image data, and where you define regions of interest in the brain. So for example, this would be a region of interest. And the idea is you obtain the time series signal, which is actually what's called boat signal. And it's the oxygen level of the brain. And you compute a pairwise association. So you've seen this picture before. So this is, for example, RI1. This is RI2. And then there is sort of the oxygen level captured over time from the first RI. This is from the second RI. And you compute the Pearson correlation between them. So what you have is that you have basically, in some sense, a complete graph between all pairs of RIs. And then their score is a Pearson correlation between them. Okay. So how to use this data and why do we use topology, right? So in some sense that in the past, what people have done is that if I have this correlation matrix, I can figure out a particular threshold Okay, so let's say I have a very simple brain network that just involving 5 different regions of interest, and then each of them has some sort of correlation. Let's say that's the weight, and we kind of figure out a threshold. If the weight is above certain threshold, I keep the edge. Otherwise, I delete the edge. So this is what's called binary. Well, I mean, we kind of filtering it, and the idea is that, well, if you just choose a particular threshold, you're not capturing the entire multi-scale information that is in the original correlation matrices. That's one of the reasons to use persistent homology is I want to look at how this graph or this network change as I change the threshold, okay? And then the second thing is that, okay, what if I just using things like dimensionality reduction? Well, if you do things sort of dimensionality reduction, such as PCA, you kind of lose the structure in this high dimensional space. So that's what is the motivation using persistent homology to study. I mean, there's more motivation why we kind of want to use topology. For example, this is a very simple example. If I project a 2-dimensional space into a 1-dimensional space, no matter how I'm going to project the points, I am losing the relation between these 2 points, because those 2 points are actually topological relation is one is enclosed in the other, right? So this is something you already know. 0-dimensional persistent homology corresponding to connected components, 1-dimension tunnels, 2-dimensional voids. We actually have been trying to do higher dimensional ones, but in this work, we actually mostly focus on 0 dimension. And it turns out 0 dimension is actually works quite well already. Okay, so the idea is, again, the classic one for persistent homology, you just start with point cloud and you grow balls of a different radius. But in this particular case, we can, so this is a classic image you can see. Left-hand side is the original point cloud. Right-hand side, I'm just increasing the radius. Or left-hand side, I'm increasing the radius. At each time the balls touch each other, the component merge. On the left-hand side, you see that the 2 red clusters merge into one another. Now you have 5 clusters. This corresponding to 1 bar in the persistent diagram. And that bar's length actually corresponding to this particular edge. Like this is really the radius where they actually merge with each other. But right-hand side, we're just showing the underlying simplicial complex representation, right? As you keep going, the simplicial complex now form a loop. And the loop shrinks by getting filled by triangles as more and more. And then this is a case where the entire loop disappears. Okay. So this is a classic example you probably see multiple times at the beginning of the semester. And this is the corresponding barcode, right? So in this case, all the 0-dimensional barcode in black, and then the 1-dimensional barcode is, is in red. And the left-hand side is just a barcode, right-hand side is a persistent diagram, where the 0-dimensional ones, because they are all born at time 0, right? All the clusters appear at time 0. So you have all the points on the y-axis versus dimension 1. This is dimension 1 feature is born at a particular radius right here, and it appears at a radius right here. Okay, so that corresponds to that. So those are just quick review of the And this is this part that you kind of seen in the previous talk as well. There is a relation basically between 0-dimensional barcode or 0-dimensional feature of corresponding to hierarchical clustering, right? So the idea, if you have, in this case, of course, 10 points, but if you think about it, there is actually an inherent connection between persistent homology, 0-dimensional persistent homology, single linkage clustering, and minimum spanning tree. And because of this connection, actually, when you just only want to recover the 0-dimensional persistent homology, you can actually recover it by computing either single linkage clustering or minimal spanning tree. Okay, so what is the idea? If you think about what is a minimal spanning tree, if I have sort of a point, I mean, in this case, I'm just using pairwise points in 2D. Okay, so this is, let's say this is my point cloud. The minimum spanning tree are sort of the tree structure such that the weight on the edge is minimal. One thing that's important to think about is minimum spanning tree is not guaranteed to be unique, because you might have some edges that have exactly same weights. So you might choose one edge versus other. But it's, number one is a tree structure. So for example, how to construct a minimum spanning tree? You first look at among all the points, what are the pairs that is closest to each other, right? And you kind of connect them. This is the first pair. This is the second pair. This is sort of, well, let me just make sure they're slightly different. This is a third pair. In this particular case, this is a fourth pair, and then this is fifth pair, okay? So essentially, you are trying to minimize the total weights of the edges that connect the nodes. That's your minimal spanning tree. But also it's corresponding to the single linkage clustering, because single linkage clustering is to say, you know, if I were going to, okay, if I were going to look at how they are merged with one another, if I start with the nodes 1 and 2, they are merged first across everybody else. And I think the next pair I said is 3 and 6, right? And then the next one is 4. Well, I mean, I'm not having the best layout, so just bear with me. And the next one is 5. Wait, did I get it right? So this is the first one. This is the second one. This is the third one. And 5 and, yeah, 5. This is the last one. And then the last two is this two merged together, which is corresponding to this edge, okay? So basically the single linkage clustering give you this kind of dendrogram, and that dendrogram also corresponds to exactly the same merging order of the minimum spanning tree. And then now you have single linkage minimum spanning tree. They also corresponding to zero-dimensional persistent homology in this metric space, because again, when you grow balls surrounding the nodes, the first time the two balls are sort of merged into one is exactly half of the distance in the minimum spanning tree edge, right? This is the next level of radius. So there is a nice correspondence between zero persistent homology, single linkage clustering, and minimal spanning tree. Okay. Any questions so far? Okay, so now let's get back to the brain network, right? So brain network, what we have is we have some form of every single red dots is a region of interest, and every edge you see here is an edge that connect pairwise. It's a complete graph, really. And then there is a Pearson correlation on each of the edge. So the first question, if I want to compute topological features for the brain network, question is what kind of filtration you're going to build on top of this weighted graph, right? So, so the first thing, did I write it here? No, I went straight to the regression part. So let's talk about filtration, okay? So if you look at the part 1 of today's lecture, if I have a weighted graph, right? This is my weighted graph, vertices set, edge set, weight. And then let's say this is weight 5, weight 4, weight 3, weight 2. This is a very simple one. And then if I want to, I mean, in that particular case, what I actually change it to is I change from weight to 1/weight. So I can kind of say that if there's high weights, that means they should be close to each other. So what I change it to is I change it to, this is 1/4, 1/5, 1/3, and 1/2, okay? And now the question is, what is a minimal spanning tree over this? I need to look at the smallest weights. So the minimal spanning tree is going to choose this edge this edge, and this edge, right? And if you think about the barcode in this particular case, what is a barcode? The barcode is going to be half of the shortest path between nodes, right? So in this case, I can have a bar that is born at 0. What time does these two things merge? It's the shortest path distance. Shortest path distance is 1/3. So this is actually, if I'm using radius, this is 1/6. And I think Ripser is using diameter, so let's also use diameter. So this is 1/6. This is the second bar, 1/5. This is the fourth bar, that is 1/4, right? That's how the bar looks like in the barcode. Okay. So in the previous work, really what the filtration is built on sort of the weight. And it's the same thing for the brain networks. Okay, you can again you can use a shortest path distance, but another one you can do is actually we actually use that in quite a few pieces of work. One type of filtration. This is filtration by shortest path. Okay, the other one is just filtration by weights directly. So if I have, again, I have the same network. If I want to build a filtration, let's say I have node A, node B, node C, node D. I can first start by just having all nodes, right? A, B, C, D. This is a filtration at time, like the first time step. And the next time step is I'm just looking at all the edges that above a certain threshold, and I decrease that threshold. For example, I start with a threshold that is 5, right? So anything that is bigger or equal to 5, so there's only one edge that shows up, because this edge is bigger or equal to 5, and the next one is bigger or equal to 4. Right, this is bigger or equal to 4, bigger or equal to 5, bigger or equal to 6. And then next one is bigger or equal to 3. So you have 4, 5, 3. And the last one is bigger or equal to 2. And that's the original graph, right? So in this case, you can just build a filtration based on the edges that is above a certain threshold, and you slightly decrease the threshold. Okay, that's how you build a filtration. Once you have the filtration, you have the corresponding barcode. Okay, so that's what we can do for this brain network. Now let's talk about a bit of a regression. In this particular case, we use what's called a kernelized partially square regression. There's other regression models that just in this particular case we use this model. Okay, so the PLS regression is considered as, you can think about it as almost like a dimensionality reduction techniques that find two sets of latent dimension from data set X, such that the projection on the latent dimension are maximum covariant. So in this particular case, my X is features from the brain images, and there's two type of features. One is a correlation matrices, one is those topological features. And then the Y, which is sort of the what we are regress against, is the EDL score. And basically, it's try to model the relation between X and Y through the regressing model. And specifically, let's say N is a number of data points, and X is sort of Y is a response, right? And X is sort of the predictor. So the idea is you decompose the X, which is your correlation and topological features, into some sort of matrix form, such that the matrix T and U is a latent variable or some sort of score, and P and Q are orthogonal matrices, and E and F are residuals. Okay, so the idea is to try to choose those latent variable, which are matrices T and U, such that the projection of X, Y onto T and U are maximum covariant. Okay. And then the idea, I mean, this is a very old regression techniques coming from 1975. It's also called non-linear iterative partial least square, is each time you try to find the first latent dimension, which is say W, you find the vectors where you are going to project such that they're maximum covariant, and then you kind of deflate the previous latent dimension from X and Y and then repeat. So this is sort of like, if you're interested, I would suggest, I'm not going to spend all the details into this particular regression algorithm, but thinking about it is sort of iteratively try to project into a dimension that is maximum covariant for my data and kind of repeat, right? But the idea is we actually want to use a kernel version of this, which is called kernel PLS. And the idea is, again, it's sort of iterative projection techniques, right? So the deflating scenario is just to say that each time I find a direction, I'm going to try to project to, I'm going to sort of factor out the sort of remaining part of my matrix K and to repeat the process until it converges. So, you know, on the very, very high level, it's trying to each time to project again into a direction that is maximum covariant, factor out the effect of that direction and pick out a second direction and repeat until there's no more sort of orthogonal direction that is, you know, that is coming out. But the idea of this is that we are going to try to put just, you can think about for the time being, this KPLS is just a particular regression model, but really the key takeaway of the work is trying to encode both correlation matrices as well as topological features into this regression framework. So you have, in this case, we have a very small data set. It's actually only 87 subjects. 30 of them is control subject, 57 are autistic subjects. And then their score goes from 0 to 21. And then the region of interest in the brain, which is also called power regions, there's a 264. So for every single subject, there is 264 by 264 correlation matrices. And you know, if you factor this out, multiply this out, this is roughly 34,000 pairwise correlations. Okay. And the idea actually, in this particular case, you can also map the correlation back to a distance. This is what you can do, is 1 minus correlation square root can be a distance. There's other ways to actually map it. This is not the only way. So actually, sorry, I misspoke because I said initially we're using this weight. This is actually a different work that we did. We're using the filtration by weights. But in this case, we're actually using filtration by the metric space embedding. But it's a different metric space embedding where the distances is 1 over correlation square root. Okay. And in addition, this is where we're using, if you, this looks familiar, this is the persistence scale space kernel. Okay. So again, every single subject gives rise to a persistent diagram, and you can use the persistence scale space kernel to define the similarity between them. Okay. And the idea is, so this is where we combine both type of features. So the correlation matrices can be vectorized because it's a matrix, right? So how do you vectorize it? You take each row and then kind of concatenate them together. Oh, let me redraw it. So you take each row, you convert it into a vector, right? So you can linearize this, and then you can compute, this is the sort of dot product, which is sort of, think about it as a similarity between two of those correlation. And now what you see here, this is a sort of topology correlation. Actually, in this case, we used both 0 dimension and 1 dimensional feature. So this K is a persistence scale space kernel in dimension 0 and persistence scale space kernel in dimension 1. So I want to take a linear combination of both 0 dimensional feature and 1 dimensional feature. So that is the kernel over the persistent diagram. But then when we actually use to them combine, I'm doing a linear combination of the correlation kernel and then the TDA kernel. So in this case, it's the weight of W1 for dimension 0 topological features, weight of W1 for dimension 1, and 1 minus those 2 to be the weight for the correlation matrix. Okay. And then you also want to compare this to against what's called a baseline predictor. And in this case, we kind of just used a very, very naive baseline predictor, which is regardless of the subject, we're always going to predict the mean adult score as a predicted severity, right? So this is just a very naive baseline. But well, there's a lot more on the statistical side that you need to tweak. Is, of course, if you think about this, I have multiple parameters I need to fix. I have those weight parameter W0, W1, because I'm using scale space kernel. I have the sigma, which is part of a scale space parameter. So again, going back to some of the students' final project, if you're using the scale space kernel, it's very important you tune the parameter. It's not always the case if you use the default parameter, you're going to get the best results. So you need to do some parameter tuning. So in this case, we use what's called leave one out cross-validation over the parameters. And if you don't know what it is, you can look it up. This is a pretty standard way. The idea is I'm going to kind of range. Essentially, I'm going to try to look at, when you say leave one out, I'm saying that in my data, because I have a small data sets, I'm going to sort of leave one out of my data and then using the rest to try to fit the parameter and taking the one that left out to try to look at what is sort of how good that prediction is, right? So in this case, for W0, W1, because it's a range going between 0 and 1, we can kind of do a grid search over the weight parameter W0, W1. And for the sigma 0, sigma 1, it's the same thing. We're going to run it over some form of grid search. And then along those things, you can figure out what is the best parameter. So in this case, what we have is this is a parameter we find. So if you look at this, this is to say that I have 0.1 to be here and 0.4 to be here, and then 0.5 for the correlation matrices. So what's interesting is that we are actually taking both into consideration 0-dimensional feature as well as 1-dimensional feature in this work. All right. And also we're going to compute root mean square error to sort of look at the final prediction. And the most important part, and then this is a part that sometimes people forget about, and it's also very important, is to say that, how statistical significant is my prediction from a random prediction, right? Or from something happening by chance. So this is where you need to compute what's called a p-value. So on the very high level, the idea of the p-value is to say, how likely is my prediction result happen by chance, right? Sometimes you just get lucky and then you get some nice, RMSE, some pretty good, prediction, like small error in terms of prediction, but it might just happen by chance. So you want to actually run what's called permutation to say that, it's actually significant. So actually this is what shows up. So the classic threshold for p-value is 0.05. So what that means is that, essentially there is this 95% threshold to say that if the value is below 0.05, it's shown to be statistical significant, okay? So the idea is that if you look at, so in this case, all this is reporting, all those 3 columns are reporting on p-value. So what you want to do is you want to kind of look at what is first of all, what is the error, which is the first column, is root mean square error, right? I mean, it's still somewhat comparable, even though there is a reduction if I combine topological features together with the correlation feature through the kernel trick, right? So there is a reduction in root mean square error. The second thing you really want to focus on is to say, is this statistical significant? The answer is yes. The only method that is shown to be statistically significant over the baseline is actually combine TDA with correlation features. So the takeaway message for this piece of work is to say that, we also tried independently to use just correlation measure, just use topological features. None of them are going to be statistically significant. So the only one that see improvement is actually combine both features together, right? So again, this goes back to some of those final project. If people are doing a sort of machine learning that uses topological features, my suggestion is to not just looking at only topological features, but looking at how topological feature combine with classic engineered existing features, how them combine to be more effective. But you have to remember, you need to kind of use compute things like p-value to show that this is happening better than chance. Okay. So essentially the takeaway from this work is we're actually augmenting correlation with topological features, give a better prediction than use correlation alone. And then this is, I put the word hopefully, because I think there's still a lot of works to be done, is that we're hopefully that the topological feature derived from MRI have the potential to explain the connection between functional brain network and autism severity. The biggest obstacle along this, right, is number one, we're using correlation matrices. What are the other alternatives to kind of extract features? There's a version called partial correlation. If you know the literature in there, there's another way of deriving sort of correlation among different regions of interest. We used 1 correlation as a distance measure. There's other ways to do it. For example, you can use things like diffusion distances. Diffusion distance. Of course, we only use the scale space kernel. There's rooms to do other type of kernels. Of course, for practical purposes, the data, the original data that's coming from for autistic patients, there's also variation among different sites. The ones that we use in this work is coming from one single hospital. But if you can imagine, when you move from hospital to hospital, the the MRI machine actually varies a bit. The condition where those data were collected do vary. So you need to actually correct for those variations among different hospitals, okay? And I think going back to this last bit, there is a major difficulty in TDA, which is how do I correlate the topological feature back to something interpretable in the original brain space, right? So if I, for zero-dimensional feature, it's fairly easy because remember, zero-dimensional feature corresponding to sort of an edge connecting a pair of nodes. However, if you think about a one-dimensional feature, this is a scenario where we talk about homologous generators. For example, if this is my very simple simplicial complex, remember, we can say that, okay, the first generator that describe this one-dimensional feature is all those red edges, but another generator, which is also describing the same loop, is coming from this green edges, right? So what's happening is that if I actually want to locate a descriptor of the area, for example, back in my brain network that give rise to a one-dimensional feature, there's a lot of variation of which one is a good representative of that one-dimensional feature. And that leads to a bit of a lack of interpretability when I say, okay, the one-dimensional feature from brain network 1 is the one that differentiate the two networks. But the question is that which area in the network are you going to pinpoint? Are you going to say, okay, it's a red circle that is responsible or the green circle that is responsible? It's unclear. So there's some effort in the field where people try to find, in some sense, the shortest loop based on sort of measure. For example, in this case, number of edges, that's one way, or the loop that has the smallest weight, that's another way. So there is different ways to try to figure out which is a generator we want to pinpoint for increased interpretability of this kind of results, right? Because you really want to, for surgeon who, for example, operate on the brain, they want to know exactly which area of the brain that they want to operate on. You can't just tell them that there's a one-dimensional generator and this is a broad area you want to operate on, right? So this is really the biggest gap, is interpretability of the one-dimensional feature or high-dimensional feature back into the original domain, and which one is mostly, can be say, this is an area that is responsible for describing this one-dimensional feature. So that is where the gap is. Okay. All right. I'm completely run out of time, so I'm going to stop streaming. Any questions? Okay. If there's no questions, I know there's a few